Tricky Topics video series. This video is spatial memory. Remembering the locations of objects and events is critical for many cognitive activities. For instance, personal memories are strongly linked to the spaces where experiences happen. This tricky topic will explore the characteristics of spatial memory by looking at some research in both humans and non-human animals. Spatial memory requires a symbolic representation of the places we visit, and there's evidence that the brain achieves this by creating maps. Traditionally, we think of maps as two-dimensional, represented on a flat surface, of course smaller than the original space. So how is this information coded in the brain? By using simple but clever strategies, researchers have discovered the existence of mental maps in laboratory rats. The existence of mental maps in rats was demonstrated by Edward Tolman and colleagues using strategically timed rewards in this complex maze. Food-restricted rats will run around this maze, turning around at blind alleys until they find the goal box at the end. Maze performance is measured by completion time and number of blind alley visits. With repeated trials, rats become faster and make fewer mistakes, as shown in this figure on the right. Tolman tested rats daily for 3 weeks under one of 3 conditions. One group had food placed in the goal box every day, so were rewarded on every trial, and the number of errors, represented in the y-axis on the left, declined predictably with training. Another group was given no food reward, so had no reason to search for the food box. Not surprisingly, they made many blind alley visits. The most interesting group was allowed to wander the maze for 10 days without reward. Then food was introduced from day 11 onward. If they hadn't learned the layout of the maze during those 10 non-food days, their errors should be similar to the rats that never got food at all. However, their performance from day 12 onward was comparable to the rats that did get food every day, suggesting that they did learn about the space, but had no reason to use this information until food was available, a phenomenon Tolman called latent learning. This study was influential because it demonstrated that rats make mental maps of space, so this sparked more research on spatial learning and memory. The most commonly used measure of spatial memory in laboratory rodents is the Morris water maze, developed by neuroscientist Richard Morris while at the University of St Andrews in Scotland. It's basically a pool filled with opaque water, with a hidden platform and a camera positioned above to record behavior. Rodents are naturally motivated to escape since they don't like swimming, so they search for a way out and eventually find the hidden platform. After repeated trials, they will typically swim straight to the location of the platform because they've created a map of space like Tolman's rats. A number of measures can be taken to assess spatial learning, such as escape time or path length, both of which decreased with better performance. This study looked at the effect of housing conditions on water maze performance in mice. Half of the mice were group housed in standard laboratory conditions, which included clean food and water. The enriched mice were also group housed with food and water, but had a larger cage, more cage mates, nesting material, paper and plastic tubes, a running wheel, and treats like apple, cheese, crackers, and popcorn. The enriched environment resulted in a shorter swim path than control conditions, an effect that was most pronounced during the first 3 days of training. This study and others using the water maze highlighted the importance of housing conditions on laboratory animal behavior and has resulted in changes to the way we house animals. Although the water maze is useful for looking at spatial memory in non-human animals, it's not feasible for testing spatial memory in humans. The Hebb-Williams maze, shown here, is a standardized set of progressively difficult mazes that can be used in both, since there is a virtual version available for humans. These traces show the paths taken by undergraduate students over repeated trials on Maze 11, females shown in red in the top panel and males in blue on the bottom. The black dots represent pauses while navigating the maze. Both men and women made many mistakes on the first 2 trials, but overall, women completed the maze less efficiently than men, with more pauses and blind alleys, evident here in trials 3 and 4. However, by the 5th trial, these gender differences disappeared. This study also tested C57 black 6J mice, a commonly used strain in behavioral studies, and compared performance to the virtual maze used in humans. They combined speed and number of errors into a single performance efficiency score, with lower values indicating better performance. The pattern of spatial learning is remarkably similar between species, including the differences between males and females. The similarity in spatial learning and memory suggests this is a fundamental skill for all species. It also allows non-human animals to be used as models of human spatial memory, which has been invaluable in identifying factors that help and hinder memory. Animal models are also used for studying disorders of memory, such as Alzheimer's disease and other types of dementia.